Hey guys, welcome back to another episode of Simuleos, the only channel on Twitch that does stuff that we do. So anyway, today's going to be a fantastic day. If you remember, last time we did physics, which was a little while ago, we were working on what's known as the Lanzas algorithm. The Lanzas algorithm is a diagonalization algorithm. However, we only got so far as to create a tri-diagonal matrix, and we were left with a little question. How do we get from the tri-diagonal matrix to the diagonal matrix with eigenvalues? Hey, iCare, thanks for coming in. So that's what we're going to get done today. Let's start by opening up Zernal and introducing the problem. Zernal. Okay, so where were we? It's been a few days, so let's kind of re-describe the problem by talking about what eigenvalues are. So we've done this a few different ways. The first way we did it was a few days ago, probably maybe 5 days ago or something like that, where we described how to diagonalize something. Now, diagonalization, let's do Asian, is the process of taking an array, which we'll say A is equal to x 0 0 x, is it 1 0 or 0 1? X 0 1 x 1 1, again these are just the indices, and turning it into something that has something along the diagonals. So this would be D 1 1 D 2 2 and zeros along here. Now, interesting thing is when we diagonalize these, sorry about that, these guys are eigenvalues. Now, what is an eigenvalue? In a physical sense, an eigenvalue. Watakanai, hola James, why is your programming scary? Tweet got me thinking. It's certainly an interesting question to ponder. Yeah, that was one thing I was thinking about last night. See, almost everything I do is apparently scary. You know, like physics is scary, programming is scary, and I didn't know why, you know, because I thought maybe, you know how like people don't want to get into a relationship if someone's like too committed or something like that? I thought maybe it was something like that, you know, like your partner or the person that you're working with, in this case physics or something like that, is just too much to handle or something like that. Like there's so much there. I didn't know. I really don't know the correct answer, but it was an interesting thing that I was thinking about at the time. Okay, so what's next? We have the eigenvalues. What are they? So let's take an array, any random array. And what I'm going to do is, since we've already done this before, I'm going to pull out my notes. And in my notes we have an array that we solved for the eigenvalues before. And actually, guys, I just realized I need to grab a small stool. Give me 2 seconds. Got it. Okay, I need the stool because I have too many things to hold in my hands at any given point in time. So let's go ahead and pull out what we need to pull out. Okay, so if you remember, a few days ago, we solved a problem with a particular matrix. The matrix was this one right here, 1 2 0. Let's see, I think it was 0 2 1. 2 1 0. My bad. Pretend I can write. 0 0 was it -3? Yeah, -3. And we showed that this splits up into a couple of different it splits up into this: -3, -1, 1. Nah, 3. Dang it. I need to keep looking at my notes because I'm getting all this wrong. Anyway, so we show this split up into these, meaning that the eigenvalues are -3, -1, and 3. Which is great. In order to get the eigenvectors, we have to do something else. We need to plug these values back in here. And by plugging the values back in here, wait 1 second, we can grab the eigenvectors. So for example, for -3, the eigenvector is 0 0 1. For For -1, the eigenvector is -1, 1, 0. And for 3, the eigenvector is 1, 1, 0. So here we have all these different eigenvectors, and I just drew them in this way. I realize this isn't standard notation. That's fine. Okay, so we have these 3 eigenvectors. Now the question is, how do we get, or what do these eigenvectors mean? Well, let's take our random matrix here, and you'll notice something rather interesting. Basically, if we take these eigenvectors and we multiply, let's see, if we do this, a times some sort of eigenvector is going to be equal to, so we multiply a times the eigenvector, it's going to be equal to some constant times the eigenvector. So let's go ahead and do this. Page, new page before. It's 1, 2, 0, 2, 1, 0, 0, 0, -3. And let's multiply it by one of those random eigenvectors. And let's just do 1, 1, 0. That was for 3. Okay? If we multiply these guys, we're going to get, and I'm going to put this sign down. We're going to get, it should be, let's see. Wait a minute. I think this is, let's see, 3, 3. And this is going to be 1 by 3. So I think it needs to be the other way around. But anyway, it doesn't matter. It's going to be 1, 2, so it's going to be 3. Then it's going to be 2, 1, 3, 0, which is going to be equal to 3 times 1, 1, 0. And in this way, we've created an eigenvector, we've multiplied it, and then we end up getting the same guy back with some sort of constant out front. Now, this might not sound cool at all, but let's do the same thing with another random vector. 1, 2, 0, 2, 1, 0, 0, 0, -3, and let's multiply it by, I don't know, 1, 2, 3, okay? This is going to give us 1 times 1, 2 times 2, 0 times 3, so this is going to give us 5. The next one's going to give us 2 times 1, 1 times 2, 4, and then the next one's going to give us -9. This is not at all equal to some constant times 1, 2, 3. In this way, any other vector that's not an eigenvector, and this is super cool, any other vector that's not an eigenvector is going to rotate and extend itself. It's going to move around when being multiplied by this particular vector, or this particular array. But an eigenvector stays exactly in the same spot. It just kind of extends itself a little bit. It does not move when multiplied by this array. And so in this way, you can kind of think, and this is maybe not exactly right, but you can kind of think of it as an axis of rotation, where everything else kind of rotates around. This vector, the eigenvector, stays the same. And that's pretty cool. In fact, this weekend when I'm going to be doing an eigenvalue video, or at least I intend to do an eigenvalue video, I'm probably going to put some sort of graphic up of this rotation because I think it's pretty cool. So it might be that after today and tomorrow, I spend a little bit of time working on that. Okay, so what's the next thing? Now, we have a question. How do we go from an eigenvector to an eigenvalue? They're both V's. But this is a vector, this is a value. We're going from a vector to a value, vector value. We can do this with something known as a Rayleigh quotient. Now, this is basically taking our eigenvector, which I'm going to denote as u, ut times the array, u, over ut, u. So what does this mean? It means basically it's the transpose of our eigenvector times the array times the eigenvector one more time over the eigenvector squared. Okay, so let's see what happens if we do this. We're going to do page, new page before. Again, the array is 1, 1, 2, 0, 2, 1, 0, 0, 0, -3. And our eigenvector, let's say, is 1, 1, 0. Okay, so this should give us 3 in the end. We know when we multiply these guys out, we get 3, 3, 0. So basically, this is a matter of multiplying 1, 1, 0 by 3, 3, 0 over this squared. So it's going to be 1, 1, 0 times, then it should be, let me think here real quick, 110. Can I ask you once again what you're even making? 1 second, Risa 401. I will finish this up and then I'll get to that. So when we multiply these guys together, we're going to get, let's see, 1 times 3 plus 1 times 3. So this is going to be, let me see real quick, 6 up top over 2 at the bottom, which is going to give us 3. Got it. Okay. So, Risa 401 just asked, what am I even making? And I'm going to talk about this in just a second. Rather, I'm going to talk about something related to this in just a second. But right now what I'm doing, Risa 401, is I'm creating, or I'm using some standard algorithms, which I just learned, by the way. They take a long time to learn, in order to create a diagonalizer. The diagonalizer will give us the eigenvalues, and with those eigenvalues, we can eventually figure out eigenstates quantum mechanically. So it should be that under the stream, let me check real quick, maybe info, scroll down. It says working with 1D magnets. The algorithm is called DMRG. That's pretty much exactly what we're going to be working on. Dense matrix renormalization group is the name of the game, but it's going to take us a while to get there, because in the end, let's see, how do we relate these two? In the end, we're going to be working on an algorithm known as dense matrix renormalization group. Okay, so dense matrix renormalization group, DMRG. Now, what this basically is we have a bunch of spins. So I'm going to draw 4 to start. 1, 2, 3, 4, just random. And we create block Hamiltonians. Now by this, I mean we take the dynamics of basically the left half and the right half, and we create a specific way in which we hold the kinetic and potential energy components of basically the energy. Now what we do here is we then diagonalize these guys. So after finding them, we then diagonalize them. And this allows us to find eigenvalues, eigenvectors, essentially eigenstates, which are, I guess you could say, elements of the state itself, the quantum state that we're talking about, which make up all other states. So it's like the fundamental states of the system. In a way, you could say these are the states, superpositions of these states can create all other states. And so this will give us the fundamental state of the system. And from here, we can continually extend the chain. From the left and the right block, we can make it bigger and bigger and bigger until we have an infinite chain of spins. And once we have the infinite chain of spins, if we put a magnetic field underneath, that is essentially a magnet, right? Because all a magnet is taking all of these spins and aligning them in the same direction. So in the end, we create a one-dimensional magnet. However, in order to get there, we have to kind of start from the beginning. And the beginning is diagonalization. The beginning is eigenvalues. Then we move on to diagonalization. Then after moving on to diagonalization, we move on to the magnet. Now, one thing I'd like to point out is that this channel is supposed to be a physics channel, right? It's kind of weird, first of all. I'm just going to take a minute to address this too. So this kind of stuff that I really, really enjoy doing, right? This is stuff that I really like, because it helps me understand things better, gives me a better, kind of like an outlet for learning these types of algorithms that I wouldn't be able to learn any other way. And I kind of took a 1.5 break from doing these types of simulations. However, I've done this for 2 days. This one for 2 days. And I did my drawing with code for like 4 days. So I think I've only been back like a week now. Yeah, about a week. The drawing with code ends up being almost twice as popular as the physics, which is a little bit weird. Hey, Screaming Chaotix, thanks for coming in. And I was thinking about why. And I think it's because the drawing with code is completely and totally understandable by pretty much everyone. Everyone knows what I'm doing. Now, that said, I don't find it as cool because I'm not doing anything, you know? I'm creating algorithms, or I'm creating like ideas in my head, then I'm implementing them. It takes no preparation on my part. I just kind of go from working on something. Let me think. How do I put this? I go from waking up in the morning to working on it. I don't spend, 12 hours throughout the previous week figuring out how to implement the algorithm, which is what I do with the physics algorithms. So it's kind of weird, but I was always thinking that the people who watch this channel would find the drawing with code kind of, boring, because there's not really anything I'm really providing there. But maybe I'm wrong. So what I'd like for you guys to do, if possible, is in the chat, let me know what it is you guys actually like. Do you like doing the physics algorithms? I know before I was going to do a poll on Twitter every day, but then I realized the polls were rigged because people who don't watch this channel were voting for particular algorithms. So it ended up being that all my physics friends who happen to follow me, all of my physics friends, they all said that they wanted me to do DMRG, but it could have been that you guys were all voting for me to do drawing with code, and I just didn't know. So if you don't mind, in the chat, let me know what you guys prefer me to do. That way I can kind of get the idea in my head as to what is more interesting for you guys. Now, with that said, I think what I'm going to do is I'm going to go ahead and keep going, because now we have a little bit more to do. A few days ago, let's do new page before. A few days ago, oops, gotta find my pen. We implemented what's known as the Lanczos algorithm. I call it Lanczos, but I'm actually not confident in how to pronounce it because there's this C randomly in the middle here. I don't know what this C is for, but that's okay. The Lanczos algorithm is a way to create what's known as a tri-diagonal matrix. Now, I know what you're thinking. Tri-diagonal matrix. Good. Thanks, Screamer Chaotix. A tri-diagonal matrix is basically a diagonal matrix with two, I don't remember what they're called, so I'm going to call them off diagonals, and everything else is 0. So it's literally a diagonal matrix with 3 lines. Okay? The tri-diagonal matrix, in and of itself, does not give us the eigenvectors or eigenvalues. However, do you have teeth or do you just sound funny? I feel bad asking. Do you have teeth? I don't know exactly what you mean, but yeah, I do have teeth. But if you're asking about my lisp, yeah, I do have a little bit of a lisp. Sorry about that. Teeth. Okay. I don't actually know why you're asking though. So, yeah. Okay, anyway, eigenvalues. These do not directly translate. Instead, in order to get from our tri-diagonal matrix, which we made last time, to our diagonal matrix, which is what we need to make today, I don't understand how not having teeth, I just don't understand the question. It's not that I'm offended by it. I just don't understand how the two relate to each other and how it sounds like I don't have teeth. Okay, what do we have then? Lanczos method, the tri-diagonal matrix. I promise you, I have teeth. Okay, let's see, what's next? Oh, the next thing. In order to get to the eigenvalues, we need to implement something known as a power method. Now, the power method, is maybe not as powerful as you might think. Basically, it's just a diagonalizer. Diagonalizer. Okay? Now, here's the thing. The power method is, in essence, simple. In fact, the paper that I read... Oops. Sorry, I dropped something. I hope you didn't hear that. It wasn't too loud. But the power method is in essence simple. I'm going to put this in front of the screen, but I don't think you can read it. Basically, the method is like 5 lines long, according to this guy right here, which is the document that I've been using to learn all of the stuff for Lanczos, Lanczos algorithm and stuff like that. Now, if we go to the next page, they give us a slightly more complicated power method that's a little bit more robust, and I'm like, okay, that's fine. And then finally, at the very end, they give us a Lanzas algorithm that seems super simple and should be super robust. And as of this weekend, I thought I fully understood it. It says, initialize Q, a random matrix of size n(m) with orthonormal columns. That's fine. For K12, do the following. Do the following. So it's basically for all of these integer values, we do the following. And then it says we basically decompose Q and R. Yeah, that was the problem I had. I had no idea how to do QR decomposition. Turns out it's not really trivial and it's not covered in too many places. So today what we're doing is we are taking a step outside of the power method for the diagonalization, and we're going to implement what's known as QR decomposition. Now, QR decomposition. Let me see. I think it's actually a lecture, so it might be freely available online. 1 second. Let me Google it, and I will let you know. So it looks like EE381V Large Scale Learning Lecture 12. Where are we? We need to go here. So it's going to be EE381V Large Scale Learning Lecture 12. Maybe this will give it. This one maybe? Yeah, it's this one. This is the one I was looking at. Okay, so it's not really a paper, it's actually a lecture note. Sorry about that. Every time I look at anything that happens to be printed out and in my hands, I just assume it's a paper. Yeah, I don't actually know what that means, sounding like I don't have teeth, but whatever. So, let me see. I actually had a really, really bad lisp when I was growing up. It was to the point that every time I'd say, like, my last name, which is, you know, has an SH sound in it, I would always whistle. It was kind of bad, but that's okay. It's nowhere near that bad now. And apparently if I focused really hard, I could not have a lisp anymore, but yeah, it's at this point not worth it. Okay, so QR decomposition. What is QR decomposition? Well, it's kind of hard to find any real notes anywhere. Oh, sorry about that. However, one thing I want to point out is that Eigen, the library that we're using, can do QR decomposition in and of itself. The problem is, in my opinion, just allowing Eigen, the library that we're using for C++ features, to do that kind of stuff, I felt that was kind of cheating. So I want to implement it from scratch before using Eigen. And so, what is QR decomposition? Well, the idea actually isn't so bad. The idea is that we take some sort of array. 1 second. We take some sort of array, right, here, and we say it's going to be equal to two values, q dot r. Out of curiosity, how do you pronounce your last name, and is it German? It is German, but it's just sh, loss. So it's like sh, as in don't say anything, sh, and then loss, as in I've lost something. Anyway, so we have a matrix A, and we split it up into two values, q and r, where r, well, let's do it this way. Q is going to be an orthogonal matrix. Now, when we say orthogonal in physics, we mean perpendicular, and in this case, QTQ is going to be equal to 1. Okay? Now, R is going to be an upper triangular matrix. This means that if we have our matrix, only these guys have values. All of these guys are zeros. It's so cool not to understand anything he says. Not like I do hear him well, but... so that's the thing. If you guys have any questions, comments, concerns, let me know. I'm trying to get to them as soon as possible, but it is true that this is a little bit harder to understand than the other stuff, which is why I posed the question earlier. If you enjoy this kind of stuff, which I do, and I think some people on this channel do. Let me know. If you don't enjoy it, also let me know. I mean, I can't change anything about this channel. I can't make it more enjoyable if I don't get feedback, you know? So that's kind of the thing. No, it's okay, Risa. You're not spamming at all. It's kind of the idea here. We're talking and learning together. Okay. So the reason we want to do this QR decomposition is because later on, when we implement the power method, we can actually super easily get eigenvectors from this. So the idea is that after performing QR decomposition, Q will be, one second, estimates of the eigenvectors. So this will be, I'm just going to notate it like this, U1, U2, U3, dot, 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 and that's fine. Let me know. I don't want to have to guess. Okay. So we have Q here. And this is going to be a representation of our eigenvectors, right? And as you remember, the eigenvectors can turn into eigenvalues pretty easily with the Rayleigh, oh, sorry about that, quotient. So U1 TA U1 over U1 TU1. And that will give us the first, hey, that true fan, that will give us our first eigenvalue. And so the idea here is that we can create our eigenvectors from this Q, and from the Q we can then create our eigenvalues. And in this way we can create both our eigenvectors and eigenvalues, and this is super cool and super powerful in physics because if you remember, like what I was saying before, I'll see you around, Risa, thanks for coming in. Like I said before, these eigenvectors are super important in physics because they hold a lot of power in terms of understanding what the arrays and matrices that we're working with actually mean. So if you have a Hamiltonian, which is essentially just a bunch of energy and potential energy in a matrix form, by doing this you can create a method, or you can work with basically fundamental states of the system, and that's incredibly powerful. And that's kind of what we're doing here in the end. So I think we're at the point now, new page before, where we can kind of write down what we're going to do today, and that's basically implement QR decomposition. From there, we can then talk about what is it? Sorry. Implementing the power method. And then we can go from there. Sorry about the yawn, guys. Okay, and that's basically all we need to do today. And I know it sounds easy. However, I have to point out that this took me quite a few days to understand. So over the weekend, I didn't realize I had to. But it did take me Monday and Tuesday to figure this out. Now, I'm working like 8 or 9 hours a day. Probably more. But with that and the QR decomposition stuff, it took me a good amount of time. So if I say something, again, that is not understandable, just stop me. Ask me a question on it. Now, if you look online for some of this kind of stuff, you'll find a Rosetta Code QR decomposition guide, which goes through a method known as the householder method. Now, that's fine, but it's almost completely unreadable because it's actually a C method. And for some reason, this guy didn't believe in actual vectors or arrays or any of that kind of stuff. He just kind of, I don't know, it's very difficult to read. So if you're trying to figure out how to do this, there actually is not, at least so far as I could find, there's not a very easily findable way to do this online. So I'm going to kind of do this in my own way, and hopefully we can get it all to work out. If we can't, we tried. So, QR decomposition. Let's go ahead and start writing the functions and going from there. I'm going to put this down here. Aw, man. The cord on my tablet is starting to fray. Okay. I refuse to believe in vectors. Well, too bad. Vectors are everywhere. Have you ever seen Despicable Me? There's a character in there, the evil villain. His name is Vector. He has both magnitude and direction. He's actually incredibly cool. Okay. I'm going to get a quick sip of water, and then we're going to go from there. Vectors were invented by the government. That's fine, but I don't know which government you're talking about. The Japanese government, the American government, Russian government, lots of governments out there. Okay, CD projects, Simulaos, and then of course we're going to go into DMRG. Do the same thing over here, CD projects, Simulaos, DMRG, LS, and you'll see we have only one thing in here, and that's lensos.cpp. Now, because this is still part of the lensos algorithm, I'm going to put it into the same file. One thing I want to point out, or one thing... No, you're fine. One thing I want to ask you guys, and it might be a weird question, but I've been putting up more, or I've been wanting to put out more YouTube videos lately. However, I don't know how frequently this should be. Ideally, sure, every week I'd put out a video. But I don't think that's feasible, just because of my schedule and stuff like that. If I continue to stream every single morning like I intend to, I don't think I can feasibly put out a video every week. So I think a video every other week is probably as good as I can get, which would mean I'd film one week and I'd edit the next week. So I'd want a video on eigenvalues, I'd want a video on or on lensos decomposition, I'd want a video on DMRG algorithms, I'd want a video on some previous stuff we did with the quantum Monte Carlo algorithm, let's see, a whole bunch of different algorithms here and there. And I'm thinking, what I want to try is doing a video where we actually go and describe an algorithm. Like, that's the point of the video. It's not like there's any physics or anything like that, we're actually just describing the algorithm. And I think that'd be super cool, because honestly, these algorithms give me a lot of physical intuition. And a lot of times, the algorithm is somehow related to physics. It's just for this kind of stuff right here, there isn't very much physics. It's actually a lot more linear algebra, which is fine. So let's go vi lensos.cpp. And of course, I gave myself a compile flag because I knew I was going to forget. And here we go there. Error, lensos, oh, I forgot a P. Okay. Now, one thing I have to point out is there are a lot of errors here. So let me see. What was it again? It was like W. It's fine. No, it's not fine. How about we do neg W no ignored attributes. Dang, I thought that was it. Maybe. Did you mean W no? Oh, maybe that's what I meant. Alright, what's the next one? It says, warning, template cast, W deprecated declarations. Let's also run with that. W no, 1 second, deprecated declarations. There we go. Okay, now the reason I did that, and it might sound kind of weird, but lately, a lot of the libraries that we've been using has a few, or will have a few problems with it, or a few warnings that pop up if we don't add these flags in there. And the only reason I want to add those flags in there is so that when we do this kind of stuff, we can actually tell where the errors are in our code. So we're ignoring the warnings for now, and we'll kind of go from there. Now, if I run this, because I know it's been a few days, you'll see we get basically a density matrix from the Krylov subspace. Again, if you don't remember, the Krylov subspace is the subspace that we created in order to ensure that the vector or the array that we create can be sufficiently, I guess, how do we put this? It can be squunched up, it can be described by a tridiagonal matrix, and then of course we created our tridiagonal matrix here. And it's pretty much what you'd expect. It's weird that we have zeros along the diagonal, but that's fine for now. We'll check that later. In fact, I'm going to leave a quick note up here saying that zeros along the prime diagonal. I don't know what this means. Okay, because it could mean a number of things. One, it could mean that it's actually working out well, or it could mean that it's not. So let's go ahead and start working on the next thing. So in here, we're going to say function for QR decomposition. And what do we need to read in? It looks to me like we're going to have a matrix XD, which is an X-dimensional matrix. We're going to call it QR decomp. Why not? And we're going to have to read in a matrix XD. And we're going to call it... Do you need to speak Japanese to study at university? No, I do not. I work at, for those of you who have not read my description, I work at the Okinawa Institute of Science and Technology. It's in Okinawa, Japan. The thing is, it is a purely English-speaking institution. It's actually meant to bring a whole bunch of people from outside of Japan into Japan as kind of a collaborative way to boost their educational process. And it's working quite well. The Okinawa Institute of Science and Technology, so far as I can tell, is pretty successful. I'd say that's in part because of the students, because I am a student, but that's okay. Screamer Chaotix, we can't have an episode of Simuleos without an OIST plug. I feel like every single day I do an OIST plug. Matrix XD, what should I call this? I will call this D-Matrix, because I'm original. Okay, now let's pop this down underneath the subroutines, and let's go from there. Now, guys, one thing I have to point out is this whole layout of my code where I kind of go through and how do I put this? I label all the functions up top, I put down main, and then I put all the functions underneath. That's fine, but it's not necessarily the best way to do it. And I'm letting you guys know that there are plenty of other people who code in plenty of different ways. Some people really, really like main to be at the bottom. I really like main to be at the top because main is where all of the, GUI code goodness is happening, and if all the GUI code goodness is happening at the front, that's what I'll know immediately what I'm trying to do, That way I know when the algorithms are called and what they're doing and stuff like that. So up here I know, okay, we're returning a matrix XD. Down here I know, okay, this is how we're actually calling it. And it helps me out. And then I put the actual functions underneath main. This doesn't matter. It's completely up to you how you do it. You can kind of think of my code this way, where we have all of this in some sort of separate header file, and then main in its own file. If I were making bigger codes than what I make in this particular channel, that's definitely how I'd do it. I'd have like main in some separate file, and then I'd have all of the header files and everything elsewhere. I wouldn't usually define global variables like I did in the in the Drawing with Code session. And by the way, I just realized I need to write down a quick note to change something in there real quick. I have to move the global variables into the class. So move into class. Okay, good. We are set to go. Okay, now QR decomposition. We'll start where everyone starts, and that is reading in Q, or reading in our D matrix. Now D matrix here stands for diagonalizable matrix, and I realize it may be a little bit ambiguous. That's fine. And actually, I just realized we're gonna have to return two different matrices here. We're gonna have to return Q and R. However, because we only really care about Q in this case, I think I'm just going to return Q for first order approximation. So we're going to return Q. And I'm going to make a note of that. Because we only need Q for the power method, I will return only Q. And I guess I'll make another quick note down here when we're defining the variables. So first of all, let's define matrix XD and make them a certain size and length. So what I'm going to do is I'm going to say matrix XD Q, and I'm going to define what it is. So Q is an orthonormal vector. Q and in this case I'll use prime q is going to be equal to 1. And we're going to set q equal to, it should be the size of D matrix. So let me see, how do we define this? We did this a while ago, matrix T, so it should be, q is going to be D matrix dot rows and D matrix dot calls. Hey Deadclism, thanks for coming in. And then we're going to put this here. Okay. Actually, I've been posting frequently on Twitter, so if you're interested in learning about what I'm doing lately, you can just follow me on Twitter. I don't post when I'm going live, because everyone knows when I'm going live. If they've seen this channel before, they know it's always 5 to 7 Japanese Standard Time. So I don't worry about that. However, I do post other things. Like I post what I'm going to be doing the night before. I post little things here and there that I think about during the day, stuff like that. So if you're interested, feel free to follow me there, and we can kind of keep up that way. I know it's kind of a weird way to do it, but I don't know. There are very few ways for me to communicate with people, and I guess Twitter is a social platform of choice, so maybe that's the way I need to do it. Okay, so we're creating matrix XDQ, and we're doing it in the way that we would expect. So let me go up here. I know that D matrix rows and columns are the same, but I had to make sure I was defining them in the right order. Now, let's also define R. And we're going to say R is the upper triangular matrix. And we're going to define R as equal to matrix XD. D matrix. Gosh darn it. 1 second. D matrix. Actually, now forgive me if I mispronounced your name. Okua Trek. The university I'm at is new. Okay, first of all, I have to point that out. The university I'm at is new, and it's only a PhD program. It doesn't have undergraduates for a reason, you know. I mean, we want to make sure that the research is as good as possible, and typically the amount of time you spend on undergraduates versus the research you get back is not a very good ratio. You get very, very little research out for the amount of effort you put in for undergraduates. But for graduate students, you get a lot of research out for very little input. So this is a particularly strong graduate institution, and unfortunately, one thing we're currently lacking in is mathematics and computer science. Now, we have a whole bunch of physicists here who do a whole bunch of code, but it's not computer science code. It is physics code. So there's a lot of stuff that you'll see on this channel. Now, that said, actually DMRG is one that they use a lot, which is what we're doing right now, or we're working on right now. So it does take a lot of understanding of computer science, but we do not actually have very much computer science here. So it ends up being that I'm the one that teaches, or let me rephrase this. We have these small things here at OIS called skill pills, and these skill pills are where we basically provide information to students. And I end up doing a lot of the computer science skill pills because I end up knowing enough to be able to help newcomers. So if that helps you out in understanding how much we actually do computer science, it's much less than I would like. But hopefully we're getting some computer science people here soon, and that should be a lot of fun. Okay, other things that we need. Let's see, we have Q, we have R. Let's just kind of go through and start the algorithm up. So the first thing we need to do is we need to scale everything. Let's see. Oh, oops. I didn't define R. Scale R to fit, rather, scale R appropriately. And then I'm gonna put a little asterisk here. Because, let's say, how do I put this? Scale R to 1, maybe? Normalize R? We're not really normalizing R. We'll just scale R. That's what I'm gonna put down. We are scaling R. I'm not gonna worry about it. Okay, so when we're scaling R, what does this mean? It means that we're taking the maximum value in R, and the maximum value again in R is the same maximum value that's in our D matrix. So we've taken our matrix that we want to diagonalize, we've set it equal to R, and now we're going through R and we're taking the highest value, and we're dividing all the other values by this highest value. And I know you're thinking that this might be a little bit of a waste of time, but just remember that in the end, we're looking for eigenvalues and eigen vectors. Um, Takanai. Yeah, actually, though, I have eaten literally the same thing for lunch since first grade. It's a sandwich and vegetables every single day. Okay, so what are we doing? Okay, so we took R, and now we're normalizing that. And when I say we're normalizing that, it's not real normalization. We're just taking the maximum value, we're dividing everything by it. And the reason this is okay, at least in my book, is because at the end here, we're looking for eigenvectors and eigenvalues. And like we showed before, it doesn't matter what these eigenvectors and eigenvalues are. We end up just, we can multiply them by any factor whatsoever. So here, we're just multiplying them by 1 over the maximum value. And that's perfectly fine in my book. Creating eigenvectors in this way is probably a good way to do it, because we're looking at the smallest eigenvector possible, if that makes sense. So the smallest subset of eigenvectors. And that's pretty useful. Okay, so scaling R, how are we going to do it? So I have this document here, and this document is from... Oh, where is it from? It's like some physics book. If I go into my history, I can probably find it. Oh, not downloads. History. Let me see. Recent, C++, low entropy. Yep, none of that's it. Let me go to history here. Twitter. No, why do I have so many Twitters? Am I really on Twitter that much? Maybe I'm on Twitter too much. Let me see. Texas, no. Reasons to vote, no. Biggest obstacle, no. Numerical recipes. This has to be it. So it's numerical recipes in physics. And that's what it is. Maybe not in physics. It's just numerical recipes. Let me Google this. In C. Yeah, this is it. Numerical recipes in C. That's the book I'm kind of running off of. Now, one thing to note about this book is if you do get this book, it's fantastic. It has a whole bunch of algorithms in it, but I didn't really know about it until the other day. Rather, I did know about it, but I was kind of too arrogant to use it. It's a very good book. It's filled with a whole bunch of good information, but all of the code in there is proprietary code. So you cannot use the code for any real project. What you need to do is you need to kind of learn the code and then write your own algorithm that uses the code. And that's perfectly fine in this case. Okay. So what are we going to do? Let's go ahead and go down here and start working on this. So the first thing we need to do is go through all of the elements of R. So it's going to be 4. And they use K here, but I'm going to use I. Int I. Oh, this is going to get confusing, I bet. Equals 0. I. Oh, that was meant to be. I less than. And we're going to put here dmatrix.rows. So let me go ahead. Yeah, it's fine. It's fine. We're going to do dmatrix.rows. So dmatrix.rows. It doesn't matter because they're both the same. I could have also done columns, but that's perfectly fine. Then we're going to do ++ I. And again, guys, any questions, let me know. I'm here to answer questions and also implement algorithms, so yeah. So let's go here and let's create a double, and we're going to call it a durable. A double, and we're going to call it scale, which is the scale factor that we're working with. It's, in the end, the maximum number. And I think, how about we call it max val instead? Because that makes a little bit more sense. Okay, so double max val, and we're going to set it equal to 0 for now. Now, I realize there are plenty of ways to find the maximum value in an array, and in fact, I bet Eigen has a way to do it naturally. So let me see. Find maximum of array Eigen. Okay, let me see. Array class coefficient-wise operation, Eigen, reductions, visitor, broadcasting. Maximum. Maximum, here it is. L infinity norm. Hoo-hoo. If you want other LP norms, use LP norm method, which is the maximum of absolute values of coefficients. Hey, Lucky Box, thanks for coming in. Okay, that's not what I wanted. A location of the maximum. Let's see. Max coefficient. Let's try it. Okay, so it says we have some sort of max coefficient. Matrix XF. Well, let's see what happens. So we want max row, max column. But I actually just want the value. Let me see. So it'll give us max at 4. Max 4. Okay. Got it. Max is equal to m.max coefficient. And then it says at max row, at max column, which I'm not sure what that means exactly. So let me just try to see if something is in the appropriate, or is appropriate here. So let's do this, and we're going to say this is going to be equal to r dot max coefficient, which I think is spelled that way. Yep. And I'm not going to give it any values in here. I'm just gonna read this out, and let's see what Eigen says about this. So let's do g++, and it actually seems to run okay. So let's go up here and put it in main. So here we have matrix xtq is equal to Lanzos, and then we're going to go through again, and we're going to say matrix xd. Do we already have d matrix defined? We do. Do we modify it at all? No, I think that's fine. And we're going to say q is going to be equal to, what do we want here? What am I doing with my life? Oh, there we are. QR decomposition. Why do I always forget? Okay, then we do D matrix. By the way, I just want to point out, I actually code basically the same way in real life as I do here, right? And so it ends up being sometimes I'll be in the middle of work and I'm just there in front of my computer and I'm typing, and then all of a sudden I just start laughing and everyone thinks I'm like looking at a funny video or something like that. But no, I'm just sitting there coding because that's me. Okay, so QR decomposition, and let's go at the end and let's see something out. For now, I'm going to comment this out because it's just a useless guy. And now we're going to see out the double. So std, see out, and we want max val, and we're going to go ahead and end line after that. Go here, g++. It broke. Oh, that's because I already defined q. So let's go up here. Hey, Fierce Deity Ninja. Fierce Deity Ninja. Wait, which existential crisis? Oh, yeah, that existential crisis, the one that I forgot about. Yep. I have one of those at least twice a day. And good. A dot out. Oh. Huh. That's not right. What are we actually printing out? I don't know what any of this is. I have no idea. There sure is a lot of it, whatever it is. Yeah, that's a hefty. Yeah, that's a lot of garbage. Yep. Ah, there it is. Yeah, I think let me try this one more time. G. Let me see. Max L should be a double. What? Let me comment this out and let's see what we get. Let's go G++. A dot out. No, we still get this. I have no idea what it is. Let's go and see what we're see outing. We are see outing this. Didn't I just run this a second ago and we did not get this? Am I see outing anything in here? No, it doesn't look like it. Oh, I know what's happening. Oh, totally fair. I'm doing this too early. Let's pop this down here. Let's do G++. A dot out. Okay, so this totally changed everything. Because Q changed dramatically. Now, let me think. What did I do to Q? Yep. Okay, so what did I do to Q to make it do this? I have no idea. It just all of a sudden freaked out on me. I don't know what these values are on top. I know that when I went down here, I defined Q as dmatrix.rows, dmatrix.calls. But that should just be a size, I think. And I don't think I modified... Sorry, I don't think I modified Q after that. Anyway, let's go up. And now let's print out the double, since it seems to be working now. Go over here, G++, and A dot out. Okay, so it says the maximum value of this array is 0.999978. Hmm. Hmm. I feel like that's not right. No, I don't. Oh, but it's of D matrix, which we're not printing out. Okay. There we go. I don't know what happened there, but let's pretend it didn't. Okay, so that's because we're printing out D matrix. But what we should be printing out is whatever we return after the function, right? So I think matrix Q. Oh man, I totally screwed up notation here. T should be the tridiagonal matrix. So here's what I'm going to do. I'm going to define Q here as tridiag. Matrix tridiag. There we go. And then in here, we're going to read in tridiag. Because that's what we want to work with anyway, right? So we're going to do tridiag there. And every time we have this Q in here, let's do tridiag. And of course, tridiag. And then put it down here too. Okay, done is done. Let's run it just to make sure it runs. G++, a.out, and... Huh. What? Okay, let me check something. So for QR decomposition, we're reading in the function tridiag. Okay? That means this is being written as the matrix XD. D matrix here. Let me... What? How am I screwing up this early? Like, usually it takes at least an hour before I end up realizing I screwed up. Okay, matrix XD, D matrix. That's what we're reading in. We have Q, D matrix.rows, D matrix.calls. D matrix is not a global variable so far as I'm aware. No, it is not. And we're totally not reading in a D matrix. We're reading in tridiag. Okay, so let's change this to something else. Let's actually change all the D matrices, so D matrices, to tridiags, because, hey, why not? Just to make... Oh my gosh, I can't do anything right. Okay, tridiag. Oh my gosh, I can't even find the M or N. Maybe that was my problem. Next, we're going to do tridiag. And what I want to do here is I want to see out R. So let me do std, see out, and I think I can just do this, but forgive me if I'm wrong here. Let's do G++. Error Q is not declared in this scope. Q is equal to, fair enough. Let's go to the top. Didn't I just run this? I'm so confused. Okay, we're going to set this as matrix XD, Q. By the way, let me check online real quick because it looks like my chat just kind of vanished real quick. Okay, good. Just make sure I didn't miss anything. So, matrix XDQ is equal to QR decomposition tridiag. Okay, let's go up here and let's set this again to tridiag. Just so, I think it's better this way. This way I know I want to put in a tridiagonal matrix. Okay, go here, G++. Boom, a.out. 74.23, that does look like it's the highest value. We're good. Yeah. Okay. Well, that's all I wanted to do today. One success is enough for today. More than I normally have. So we're getting there. Now, one thing I have to point out is the code that's available on the... what was it called? I just brought up the book. Numerical recipes book. If you're looking for the code available in that numerical recipes book, note that it is in C and it's using some different libraries. So this is not as easy in the numerical recipes book. So going through the numerical recipes book, if you guys happen to want to buy it, not saying you have to, in fact, I am somewhat discouraging you from buying it unless you're super into computational physics and you really, really, really want to move the next step. It's going to be a little bit more difficult to read. So let it be known that there's going to be a lot of boilerplate code. And you have to kind of figure out what that boilerplate code is. The reason I bring this up is because this right here was like 5 lines in their stuff. Okay, so here we go back to the for loop. And let's go from there. Okay, so we have the for loop. In this way, we've just found the maximum value. And what we want to say is if max val, let me see, if max val is equal to 0.0, we're going to say that it's singular. So I just want to set that singular equals true, which means we have to define what singular means, and that's going to be up here. So where do we define it? We define double max val here. So let's define Boolean singular. Now, in this case, I don't expect that we're going to run into a singular matrix, but it's nice to have this here. But your streams are both very interesting, and also make me burst into laughter when you're coding and speaking at the same time. Oh, why would I be offended by that? Your streams are both very interesting, and also make me burst into laughter when you're coding. That's fine, right? Sorry if oh, you're saying that I'm randomly mumbling while... Maybe I could stop mumbling while streaming, I guess. I don't know. Anyway, let's keep working on it. So singular is equal to true. And then we need to do one more thing. And what they do here is something a little weird. And I don't exactly understand it. So what I'm going to do is I'm going to create a whole bunch of different matrices. And these are going to be matrix XD, but it's only going to be one column wide. So they're going to be vectors. And I'm going to define these here. Defining vectors for algorithm. Now these vectors should all be, if I'm not mistaken, of a particular length, which is the same length as the other ones. So let me check real quick. It looks like we have, let's see, vector C, vector N. Yeah, they're both of the same thing. I'd rather you talk and explain rather than silently doing stuff. Yeah, I'm trying to talk and explain, but I gotta be honest, like it's kind of difficult to do both at the same time. Okay, so what we need to do is define a couple of different vectors that we'll be using throughout this system, throughout this algorithm. Now, I will be honest, I don't fully understand what all of these numbers, this notation means. So in this guide that I'm following, it says C and it says D, which by the way, as you know, I'm not a big fan of single lettered variables. I think they're kind of useless. However, thanks Lucky Box. However, in the case here, I'm fine with Q and R because they're capital Q and capital R, and the name of the algorithm is QR decomposition. So I figure that's pretty easy to figure out. But in this case, they just have like a random vector. So I'll show you what they have. It's matrix XD, something like this. C, which is of size, let's see, I think tridiag dot rows. Yep. And then 1. So it's a vector. And then they also have D, which is again tridiag dot rows and 1. This doesn't really help me very much. Hey Dave, what's up? But I'm pretty sure these are what's along the diagonals. So I'm actually going to call this diag, because I'm pretty sure it's what's along the diagonals. I don't know what C is. However, I don't want to just keep it C because I can't figure out what C means. So what they do here then is they set all of these guys equal to 0. So we're going through all the K's and we're setting them all equal to 0. No, not exactly mumbling. It's more that you speak out your thought process, and from the time to time produces funny sentences. Yeah, I end up interrupting myself all the time. Like what I end up doing is every time I'm coding, I look at the code and I'm like, ah, this is super cool. Then my eyes kind of wander around as I'm coding and I look at things, like chat. And then I'm like, I will interrupt myself, whatever I'm saying. I know that's a problem and I have been trying to fix it. Another thing I try to fix is the number of uhs I say, when I'm doing something like, well, that's good. At least you're working, right? A lot of my friends have not been able to get a stable job. So you're doing well for yourself. Yeah, so right there. I just did it again, where I'm saying something and then I interrupt myself and I forget what I was saying before. I do that a lot. Okay, so I guess I'll leave this C for now. How many other C's do I have? C? See, look at all these C's. If I'm just going to search to replace C, there's no way I can do that. Okay, let's go down to the bottom, and let's change C to jury. I don't know. What should we call it? We'll call it. We're gonna call it C-diag. Because I think it's along the diagonals too. I just think it stands for something. I think the C stands for something. So we have diag and C-diag, and these are both vectors. Now, what they do is if it is singular, they set all of the diagonal values equal to 0. So they do C of K, which I think is called this way, right? Forgive me if I'm wrong, because I'm using I. And this is going to be equal to, so it's C-diag of K is going to be equal to diag of K, which is going to be equal to 0.0. Okay, and let's see what happens if we run this, just to make sure I did that correctly. Oh, I put in K's, I need I's. Oh my gosh, this is not going to turn out okay. G++. Oh, what happened here? Let me see, how do I call individual values? I forget. Maybe it's parentheses? Oh my gosh, it's like the easiest thing in the world, and I'm forgetting how to do it. K was not declared. dmatrix.rows. Okay, let's just do this. dmatrix.rows. Try diag.rows. And let me see it. Let's change these guys to parentheses. Maybe that's what I need to do. But let's write it, and let's G++ real quick. Yeah. Okay, so let's change this to a parentheses, and this to a parentheses. Oh, I've used this before. Let me scroll up. How have I not? Rows, alpha of 1, 1. Yeah, so it's parentheses, not boxes. Here we go there. Here we go there. Now let's try it. There we go. Okay, so they set these equal to 0, which again, I'm guessing is some sort of diagonal thing, but if I figure out what C is supposed to mean, I'm going to go back through and fix it up. Okay, so now, if maximum value is equal to 0, that's what we do. But I'm not expecting that to happen, so we have this big else statement. And in the big else statement, we have a whole bunch of stuff. So let's go through and see what we need to do. First thing we need to do is we need to go through and divide everything by the scale, which is going to be our max value. So it's going to say 4. In this case, because we're already in the I loop, what we're basically doing is we're going to the upper diagonal, right? So we're going to say 4, j is equal to I. Oh, I need an int in front of here. And I should probably be using size t's here. Yeah, maybe I should be using size t's. Let's change this to size t. Again, this doesn't really matter. The difference between size t's and ints is just that size t's cannot be negative. But hey, why not? So size t. And then we say, I think j less than n, which is going to be try diag.rows. Then we're going to do plus plus j. And now we have a second loop. Okay, now this is a little bit weird. I don't like having this inside of an else statement, but that's fine. We'll keep working on it. So now what are we going to do? We're going to say that... See, that's why I don't like it. We want... It should be R of... And what they have here is IK, which for us will be JI. Doesn't matter in this case. So what does this mean? We're going, let's say J is equal to 5 or something like that. Or I is equal to 5. Then we're going from 5 to N. So 5 to N, right? So RJI. Let me see. So that should be, I feel like it should be IJ. Let's do Rij. Is going to be equal to whatever was before. So that's going to be Rij. Yeah. So Rij is going to be equal to R of Ij divided by the max value, which is going to be what we have defined before. So max val. Okay, good. Also, my chat seems to keep... Are you guys okay in terms of lag? You guys are fine? Let me check online real quick. Because my chat seems to keep disconnecting and reconnecting. So that could mean a number of things. It could mean that the stream's kind of going in and out. So let me know if that's happening. Okay, so here's what we did. We just normalized this particular row. And you know what I want to do? For now, because I don't really care about the efficiency at this point. No, I should probably leave it this way. This is fine. We already found the maximum value. It's fine. Okay, so next what we do is after this for loop, which isn't very long by the way, we then say we create some sort of sum, which is going to be equal to the square of different things. So let's do here. And it's going to be that the sum at up here is equal to 0. So let's see. Sum is equal to 0.0. And let's go down here. So now what we do is for same loop as we had before, size t. Actually, why don't I just use, it is less than n. It is the same exact loop. Okay, let's just go into this loop. Why not? Okay, so what we're going to do is we're going to say sum plus equals, and then we need to do the square of the previous guy. So this is going to be Rij times Rij. Right, so now we're adding everything up and squaring it together. This is the sum, okay? What I need to do is I need to add a quick comment in here saying I may have mixed up the indices. Because I may have mixed up the indices. Okay. Now, what's next? We have this. We have the sum. Everything should be fine. So now we have to define what's known as sigma. Sigma is going to be another double value. Luckily, we define it here. So let me add sigma there. So here's sigma is going to be defined as... let's see. It's going to be equal to... 1 second. Yeah, so this should be right. It's going to be equal to what they call sine, but it's not actually sine. So let me go in and see if I can find a sine function in C++. It should be in math, I would believe. Is there a standard sigmoidal function, whatever it's called? Let's see, return type t sine. Surprised no one has posted the branchless, typeless C++ version yet. Let's see, x greater than 0 minus x less than 0. I have to run. My brain is urging me to get some sleep. Alright, Watakanai, I'll see you around. Have a fantastic evening. Don't worry about reading the lecture notes. I mean, we'll get through it eventually. It'll take a few days, but we'll get through it eventually. Again, this is kind of... The streams here are kind of, in a way, more relaxed than other streams, you know? I work on things at my own pace. And hopefully you guys learn things in the process. That's kind of the hope. But Watakanai, thanks for coming in. I do appreciate it. Have a fantastic evening. Okay. I'm just gonna do this. I'm just gonna create my own function that is sine. Go up here to the top, and it's going to be int sine. And it's going to take in a value, and that value is going to be a double value. I have fun reading and decoding the math behind it. Yeah, honestly, I do too. I find it weird. Again, I'm going to sidetrack one more time, but a lot of my friends are super into video games, and that's fine. A lot of people love video games. But like for me, I really enjoy programming, and I think I enjoy programming just as much as they enjoy video gaming, and I can't express that to them. I don't know how to show them that it can be fun. Doing programming, doing math and stuff like this, doing things that I would consider productive can also be fun. And I think it's kind of a problem in our educational system. You know, we treat anything that is, well, I would say scientific, anything that is, you know, problem solving, we treat it as something you have to do, not as something you should want to do. And it ends up being that then anytime they should be doing that outside of, you know, work or whatever it is that they typically do, they don't want to do it. And for me, it's like, this is super fun. This is super cool. I'm learning so much stuff. It's great. And for them, it's like, what are you doing with your life? Why are you spending your free time doing work? And I don't know. It's just, I just wanted to point out that different mentalities, different strokes for different folks, as they say. I think that's a phrase. Oh gosh, I hope that's a phrase. Has to be a phrase. I'm assuming it's a phrase. Function. Function to return. And it should just be -1. It should just be the sign. It's literally sign. But it should be called, is it the sigmoidal function? Signum function. Sign. Value. Signum function. Okay. So let's go down here and let's create it. Down at the bottom. I'm surprised it doesn't have this already. Okay, so we're going to do basically what the other guy said. Clearly, my mom keeps asking me to take summer vacation and have fun, but math and programming is what I enjoy. Alright, well, have a fantastic evening. Sorry for holding you. Yeah, Lucky Box, it's weird. Like, I'll be honest, I do enjoy playing games with friends. I really do. So, like, Super Smash Brothers, I'll play. Guild Wars, I'll play. Super fun games when you're playing with friends. But I can't play games on my own anymore. I have to, I don't know, I feel like I get super sad when playing games, actually, because, like, I'll be playing the game and then I'll realize I'm not doing anything but playing the game, and I don't know, I just get sad. Okay, so sign. Basically what we're going to do is something super simple. We're going to say if value is less than 0, we return 0. Actually, why don't we just do a switch? Why not? Switch. Oh, but it's a double value. Ooh. No, this is the best way to do it. If statement before. If value is less than 0, 0.0, why not? Then we're going to say else if value is greater than 0. And then finally else, which would mean it has to be equal to 0, right? No, their else case exists. So let's do this. Return. What do we want? What do we want? We want -1. What am I doing? And here we want +1. And I don't know if the signum function actually returns 0, but in this case we're going to return 0. This is the simplest, most intuitive way to get the sign function. Okay, so now it's going to be sigma is going to be equal to what they call sine, but in their case sine is actually a times the sine of b. So in this case it's going to be, one second, sigma is going to be equal to the square root of sum. Do we have square roots naturally in C++? Let me see. I think it's in math. Has to be in math, right? It is in math.h. Okay, that's fine. It should just be square root. Okay, let's go up to the top. Add in math.h. Include math.h. Go down to the bottom. Thanks, Clone Style. And let's pop down here and let's go ahead and do this. So the first value is going to be the square root of, one second, the sum that we just created before. And you might be asking, why did we add everything together? Why did we add the squares of everything together and then square root it? This is because this is the L2 norm, which is basically x squared plus y squared plus z squared, the square root of that. Now, it's going to be square root of sum times the sine, and I'm going to put a double here. Double of the sine of, what do we want? RKK. So this is going to be R of I. Okay. Now, the reason I did this way was because in the end, we're probably going to need a double. And this should probably make a good bit of sense. Okay, so now we have sigma. And now what we're going to do is add sigma to each of the diagonal elements that we're working on. So we're going to say that r of I is going to be plus equals sigma. And let's pop down here and change this to a capital R. There's a way to automatically capitalize in Vim, but I don't remember what it is. There's just a letter command that you run. Okay, R is equal to that. Now what we're going to do is we're going to work with this C vector that we were working with before. So if you remember, I call it C diag, and it's going to be equal to sigma times R of I. Move down here, and now we're just going to change diag. Oh, shoot, I forgot. Of I. And of I is going to be equal to minus the scale, which is going to be minus our max value, times, and this one should be our II. Okay. Oh gosh, how far are we going to get today? We don't have so much longer. I mean, we do. We've got like 40 minutes, so we have plenty of time. I think it was like G something? What do you mean G something? I'm not sure if I'm G something. Is there a function called G something? Maybe. I'm not sure. Okay. So minus scale times sigma. Now we have to do GU. I'm not sure. Oh, the Vim command. Oh, maybe. But G usually stands for go somewhere, right? So it's usually if you type in like G10G, it'll bring you to line 10. You know, I think. Oh, what is it? G? I don't remember. There's some way to do that. I always insert different commands. Okay, so now we have to do another loop. And this loop's actually going to be the same loop that we ran before. So it should be for, you know, it's going to be for, let me see if I can get this right. Basically through all of the elements we were working with before, except, yeah, so this should be fine. Let's see if I can do this. For size t. Should be the same thing. J equals I. Then we do J is less than tridiag dot cols, no, rows, plus J. Man, I've been doing J++ for so long, the plus J's just look so weird to me. And I realize they're basically the same thing. They're basically the same thing, but I'm trying to do better practice, you know? So I'm trying. So now it's another loop inside of here, and it's going to say, at this point, we should reinitialize sum. So for each of these guys, we're going to say that sum is going to be equal to 0.0 one more time. And now we go through, and we say for another guy, which I'm going to call k, size t, k, equals, in this case, it's going to be equal to I. Then we're going to say k, sorry, is less than tridiag.rows. Then we're going to say k++. Okay. So what are we doing here? We're basically going through, let me see if I got this right. We're going through, and every time we pick a new J, we basically go through and we look at all of the elements along that row, right? So it's kind of like we're taking the top diagonal of our matrix up here, and we're picking a J, right? And after picking a J, we then take that entire row and we look at it, you know? So I hope that makes a little bit of sense. Maybe it does, maybe it doesn't. Okay, so we have this, and we're going to say sum is going to be plus equals basically all the squares like we had before. So R of k, I think it's ik, times R of ik, and then we say tau, which is a new variable, but hey, that's okay, is going to be equal to the sum divided by c of k. 1 second. So now we say tau is going to be equal to the sum that we have so far divided by c diag of And I said K before, but this is actually I. Okay. This is getting kind of confusing, and I understand if you guys have questions or anything like that, just let me know, and I will try to answer the questions as best I can. Now what we do is we go along and we say, for I equals K, I plus plus, wait a minute, let me check this real quick. So we have, this is our sum. Sorry about this. So the sum ends here. And then we basically do the same loop again here. So let's grab this for loop. There. And let me go up to the top and define tau, which I have yet to do at this point. So Boolean, matrix, sc die, what am I doing? It should be for this loop, right? Oh, here's the double, tau. Okay, now let's go down here. Tau is equal to sum over it. Oh man, I did this wrong again, freaking. Okay, let's add this guy up here. What we're supposed to do is define tau in between the two loops. And I failed to do that. Sorry about that, guys. Okay, now we have this defined. Let's now do the last thing that this loop is for, which is going to be, sorry, our, what they have defined as ij, which in this case should still be ij. Yep, let's try it. So we're going to do ij, and this is going to be equal to, minus equals. It's the two toggle characters case for lower. Oh, okay, let me try that in just a second. Thanks, clone style. So it's going to be minus equals tau times r of ik. Now again, I'm not. Okay, so you're saying it's. Oh. Huh. 1 second, let me see. Did that work? Oh, it did work. Fantastic. So let's do tilde. Oh, okay. Wait, what? Oh, it just switches cases. Neat. Haha, they're all caps now. It's like I'm writing Fortran. Okay, fantastic. That's actually super cool. Thanks. Okay. So in this way, we have now created the matrix we need to create. It's all kind of set. So now all we have to do is set the diagonals one last time, and we're done. But this, basically what we've done here is we have set up the R matrix to work with from now on. So from this point on, we're basically just working with the Q matrix, and then we're coming back to redefine the, you can also combine, yeah, I'm sure you can. There are a whole bunch of neat, what's called Vim Golf. I don't know if you've ever heard of it before, but Vim Golf, let me look it up. Vim Golf, and I'll show you guys a link. Yeah, so these are basically ways in which you can use Vim to do certain things, and you try to do it in the least number of commands. So like, you go to a line, you delete all these kind of things. It's kind of a very interesting thing that I've never been good at, but if you're interested and you want to learn Vim, it's an interesting way to learn. Okay, so now we have to do one more space. Now what they do here is they do this singular thing again one more time to check to see if it's singular. And I guess that's okay. We're going to do that. Right? It is pretty cool. So we're going to say D of, you know what I want to do this whole time? I want to define a new integer value. Where do I define my ints? Do I define any ints? No, I do not. So I'm going to say int. And what do I want to call it? I want to call it row num. That's fine. Is going to be equal to try_diag dot rows, and add this in here. Now what I want to do is I want to search and replace all of these guys. It's crazy how much power Vim has. Yeah, that's the thing. So a lot of people, Vim and VI are incredibly powerful, and I mean I use them because I can work incredibly quickly with them. But a lot of people don't, I guess you could say, a lot of people don't use them because they're kind of like terminal editors in a way. So you get used to it, and as you get more and more used to it, you get better and better with it. And it's kind of neat, you know? So this is what I'm going to do. I'm going to search and replace. So this is just a simple command. Search for try_diag.rows, parentheses, and I'm going to replace it with row num. And I'm going to ask for permission every time just to make sure. So this one, yes, I want this one. Yes, that one. Matrix XDQ. Yes, want that one. Yes. Right? Yeah, it should be okay. Yes, 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 yes. Hit return. Okay, let me do it one more time because I think I missed a few. Okay, so let's do s try_diag.rows with row num. And let's do G this time because I'm pretty sure that's okay. Okay, this should be set. Yeah, so that's just what the C does instead of the G. So G is for global, C is for C. I don't know what C is for. Okay, so we're going to say row num. Sorry about that. Screwing this up. Row num. 1 second. Row num is going to be equal to. Yeah, probably confirm. Yeah, you're probably right. And this is going to be equal to R of row num. Row num. Okay, now what we're going to say is if it's going to be D of row num equals 0. Let's do 0.0. We're going to say, what do we want to say? Sing equals true. Now let me just very quickly compile this because I probably, yep. Row num was not declared in this scope. 51. 51. Yep, that's what I thought. I knew I screwed something up. Try_diag.rows. Where's the next one? It should be 151. Yeah, dang. I knew I should have done it globally. Try_diag.rows. I missed a semicolon on line 177. Well, 76 rather. Let me see. D was not declared in the scope. That's because it is diag. Let me see. What do we have here? Diag and diag. Right over here. And let's do it one more time. This one doesn't quite compile. Expected a parentheses. Sure you did. Diag of row number. G++. Try.rows. Where are we? 51. It's because I forgot parentheses. 1 second. And done. So all those errors are fixed. Let's keep working on it. So now the next thing we do, and I think we might be able to get the skeleton of this completed by the end of today, and then we can actually run it and see if it works tomorrow. So I think that's how far we can get. Let's see if we can do that. So now what we need to do is set up Q explicitly. Set up Q explicitly. Okay, what do we need to do? Well, let's start. So now we have to go through some for loops. Again, we're out of all the loops right now. So we probably need to go through some sort of loop. Now, one thing that I find rather interesting here is that he sets up Q transpose as equal to the identity matrix. So what we should probably do at the very start when we set Q up initially is set it up as the identity matrix. Now, I don't remember how to do this, but I know we've done it before. So I'm gonna look for identity. And let me see, identity, identity, identity. Here we are, look at that. I'm good. So now let's go down to the bottom and let's define Q as equal to that. Let me scroll up a little bit. Where are we? Diag, here it is. Q is this. So now let's, I guess, delete this and put it here. Q. There we are, matrix XD identity. Let me run this just to make sure it works, and it doesn't. because D matrix doesn't exist. Try diag. And try diag. And I'm going to change this guy to an equals with that because the dots were driving me nuts. Okay, Q explicitly. So we already have the identity matrix set up. Now we just have to go through everything and go from there. So here's... Let's just do it. So if... No, rather, for loop first, for. And it should be, would they have k, or I'm sorry, int I equals 0. I is less than what should be number of rows, and it is num rows plus I. So first loop down, next one. We now have the question, is the C diagonal, which is our guy up here, is that guy equal to 0? If it's not equal to 0, we can continue, else we don't do anything. So if C diag of I not equals 0, 0.0, then we continue. Okay, now in here, Vimy Lisp. This has to be the most hardcore programming stream I've seen in a while. Xterm, Vim without syntax highlighting, and chat and IRSSI. Thanks, Vimy Lisp. Or is that Vim My Lisp? I don't know. Either way, I'm using Vim. I have a slight Lisp, so it works out okay. And actually, I'm not using Xterm. Just for the record, I'm sorry. I know you thought this was a hardcore stream. I'm actually using a terminal known as Sakura. So it's like the Japanese cherry blossom. And that's the name of the terminal. I just got used to it. Super fun. Okay, what am I doing? C diag not equal to 0. We continue from here. Now, what they have us do initially is set the sum equal to 0.0. And let's continue from there. So we have the sum equal to 0.0, and now let's go through and fix everything up. Now they do something, I don't like this code that I'm looking at right now. Just don't like it. Because they keep not putting curly braces, and it's driving me nuts. 1 second, I need a quick sip of water. Sorry about that. Okay. So, what do we need to do? Let's just continue. I think we can get all of this written. And then tomorrow I'm going to go through and explain everything one last time. Just to make sure it all makes sense. And we're going to try running it. Tomorrow we're going to run it. Today we could also run it, but I think it's going to break today. Just because of luck. Okay, so what do we need to do? Let's go from here. What am I doing? Gosh darn it, I always forget what I'm doing. Okay, so 4. Let's see. It should be int I, or let's do int k equals I. Again, we're just going through the upper diagonal. I is less than k, sorry about that, is less than n, which is going to be our number of rows. Row number, sorry about that. And then we say plus k. Boom. Getting there. Now what do we do? What we need to do next is we need to say the sum is going to be plus equals, 1 second. Sum is going to be plus equals r of, oops, sorry about that, capital R. Oh my gosh, can I do this? I don't think I can. R of ij. I missed something. I totally missed something. There's an additional for loop in here. Sorry about that. For int j equals 0. J is less than, should be number of rows. It is indeed, except it's row number. Then we do j++ or ++j. Then we put this all into a fantastic curly bracket here. Okay, so now we've got a couple lines here that we need to indent. I'm going to set number. And I'm going to say we're indenting, let's see, 1, 2, 3, 4. So from 205 to what looks like 208. S. we're going to add in at the very start, which is what the caret means. Real quick, where's the caret? 4 spaces. There we go. So set no number. Good. So now we have all that set, and let's go from there. So r of ij times, which should be q of ij. Is this right? No, I think this is q of ik. Okay, so what are we doing? We're basically going through all the upper diagonal of R, and we're multiplying it by Q. Now, Q, again, was set before to just be the identity matrix, so this could probably be sped up significantly in other ways, but we'll work on it from here. So now what we do is we go down here, and we say for int... Oh, I'm sorry about that. I have to do one thing real quick. The sum is going to be divided by C diag of what looks to me to be I. Okay. Now let's go down here and let's do the last for loop. So for int, this is totally going to break when I run it, int k equals I. Let's do 1 second real quick. What am I thinking about? I don't know. K is less than row number. Then plus plus K one more time. Pop down here. And add another guy here. What we'll say is Q, capital Q, make sure I have a capital Q, good, of, 1 second, Q of ij is going to be minus equals the sum times R, big R of ik. Now I think I screwed up the indices somehow, and I'm gonna have to go back through and check those. But that's basically the for loop for Q initialization, and now all we have to do is remove... Wait, is that 4? That's 4. Remove lower diagonal from R. So at this point, guys, we're almost done. We just have to write this last thing, and we've done actually everything we need to do for QR decomposition. Again, it's a matter of getting R ready, then forming Q, and then deleting the lower left of the R matrix. So it's going to be 4. Let's do int I equals 0. I is less than number of rows. Row number. Doesn't matter. Plus plus I. Then we hop down here. Now guys, this is the function, but it's going to break. I'm just letting you know that ahead of time. It's going to break. So R of what they have here of II is going to be equal to D, so diag of I. And this is why I called it diag to begin with. Now we say for, 1 second, it should be int k equals 0. K equals I, sorry about that. K is less than number of rows. I did it again. Row number plus plus K. And then we hop down here and we do this. We say, 1 second, R of I, 1 second, K, I think this is right, is going to be equal to 0. So this is again setting everything else to 0. 1 second, ij, I less than I. Oh, that's because I did this wrong. Ah, good. I was super worried here. 0. I. Okay, so we have our R matrix, we're setting all the diagonals, and we're removing the lower left. And I'm going to say lower left instead of lower diagonal, because that doesn't make any sense. Left. Okay, So let me go ahead and compile this because it's probably going to break. Okay, let's see what happens. G++. Okay, forgot a couple of semicolons and stuff like that, but it doesn't seem so bad at this point. So let's go to 202. For int I equals 0. Num rows. How did I get this screwed up so many times? Okay, then forgot a semicolon at 208. Pop here, add a semicolon there. Write this, go over here, G++. Okay. Well, guys, we have 15 minutes. This is as far as I wanted to get. I guess we'll leave it at a cliffhanger. No, we should probably run it. Okay, we'll run it. That's what I thought. Okay, it broke. Now, we could use GDB and go through and debug it, or we could just print stuff out, which is what I'm keen to do. Man, I feel like we should do this tomorrow because we don't, at this point, we're at a situation where I've got like 10 minutes left in stream, right? And I'm thinking to myself, okay, well, we can do this tomorrow and we can just go through and debug everything. Or I could even debug it tonight because now that I have a decent understanding of what we're actually doing, instead of reading up, what I can actually do tonight is, what you call it? Do a little bit of programming and or something like that. Now to do that, I'm going to have to commit this to GitHub, which is perfectly fine. It's not currently working, so I don't like committing things that are not working to GitHub. But then again, my entire stream, I've been committing stuff that doesn't work to GitHub, so it's fine. I'm not so worried about this one repository being a little bit malfunctioning. So let's go through and see if we can see out some stuff real quick. So obviously before this for loop, everything seems to work because we've outed a max value. So what I want to do is I want to actually just see how far we get with these different iterations. So let's just go through here. And I'm going to say std cout I end line. This is going to be great. Now we have this additional loop in here where we do the j's, and then we have this guy in here where we do j's again. So let me do a loop in here, and let me do std cout j end line over here, and we're going to do g++, and then a.out. We're going to see how far we get. Okay, as expected, we don't get through the first iteration. In fact, we don't even get to this cout of j. We only get to somewhere in here. So let me go up here and let me see how far we get. So we have std cout I. Let's just see out in here, see what happens. So std cout, and what are we going to say? Stuck. End line. Let's go here. G++. A.out. We were not stuck. Fantastic. Okay, else. So it's probably stuck in this loop then. So let's print out. What did I just do? What? What does P do? What am I printing out? Stuck? What? Okay, I never knew what P did in Vim. That's interesting. Apparently I'm really good at just pressing the P button. Okay. We're gonna need one of these anyway. Okay, so now we're gonna say J. G++. A.out. That's what I wanted. Actually, let's do it this way. J equals, and then we set J. Oops. J.out or A.out. Let's go. Okay, J equals 1, 2, 3, 4, 5. How far is it supposed to go? We're at the first iteration. How big is this matrix? This matrix is like 200 by 200, isn't it? No, 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 no. This matrix is 1, 2, 3. No, wait. 1, 2, 3, 4, 5. 5. We got it. Yeah. Oh, wait. No, we didn't. Let's minus 1 to all the row numbers. Int row num is equal to row num? What does that mean? 1 second. Try diag dot rows. G++. A not out. Okay, we got further. We got further. So, for the record, remember before when I did that global change of all of the tridiags to be row numbers? Well, I changed the initial definition of row number to be equal to row number, which meant it wasn't equal to anything. Okay, good. We're working on it. What's happening with these i's? We're only printing out I up here. It goes 0, 0, 1, 2, 3, 4, 1, 1, 1, 2, 3. Are we see-outing anything else? See-out. Max fell, that's fine. I, J. Oh, we're doing this J too. And it breaks at some point. Huh. Okay. Again, this is a perfect situation for me to use the new debugger. That's GDB. I'm not going to use GDB. Let me check real quick. Okay. I thought for a second I was missing some chat messages or something. Anyway, if you guys have any questions, concerns, or anything like that, let me know. What I'll probably do is if I have some free time tonight, I will go ahead and debug this tonight, or I'll work on debugging it tonight. So I think I understand what the problem is, and then we'll keep working on it from there. And I'll kind of be working on it till the end of stream, but I kind of wanted to take a second and talk about something that I talked about at the start of stream one more time. And I realize if you're watching this on YouTube, you'll have heard this discussion twice, and I apologize for that. But a lot of people here on Twitch have only heard this once, or maybe they've heard it the whole time. But I'm actually curious. I really want to hear your guys' feedback because this stream is kind of a weird stream on Twitch. I will totally admit that. It's on Twitch Creative right now, which there's a whole bunch of reasons we're on Twitch Creative, and I'm not going to go into that now. But we're on Twitch Creative with the hashtag programming. Another hashtag that I always add to my videos when we're doing physics is hashtag physics, which, for the record, is not a community on the Twitch Creative side. So basically, with Twitch Creative, you have all of these like hashtag programming, hashtag drawing, hashtag game dev, or whatever, and all of these hashtags are like little communities inside of Twitch, right? And the communities that I always work with are programming. And then when I've been doing the drawing with code, I've also been doing hashtag programming. The physics hashtag is not an actual hashtag, and I've been thinking about making it an actual hashtag, but I'm the only one on Twitch that does physics. So far as I can tell. So that means I can't make it a community if I'm the only one doing it, and it's only up for 2 hours a day. You know what I mean? So I'm just going to kind of continue to stream with the hashtag physics, and that's not so big of a deal. But my question to you was, what do you actually want to see on this stream? Before we were doing the drawing with code thing, which was, by the way, a lot of fun. Now we're doing more physics again, and again, this stream is completely based off of physics. Or mostly based off of physics. So I just want to hear your feedback. What do you want? Do you want me to work more on programming stuff? Do you want me to work more on physics stuff? You know I was gone for like a month and a half, but I'm back now. And I'm kind of debating what we should focus on. In my opinion, we should always focus on physics because I'm always more motivated to work on physics than I am to work on other things. But that said, it's also you guys. You guys have some push and pull. So if you guys have something you want to say in particular, let me know. I mean, I can't do anything without feedback. So you can send me like a direct message on Twitter. You can send me a whisper here on Twitch. If you can do whatever you want, just send me some sort of information. I even have a form that you can submit. It's like a Google form or something like that, and we'll go from there. So just however you want to, send me some messages, and we can totally work on whatever it is we need to work on. I see Clone Style likes physics though, so that's good. It's up to you, Clone Style. If you want to start streaming, by the way, guys, if you're not aware, Clone Style is a streamer also. He does a lot of cool stuff. Feel free to check out his channel too. But yeah, if clone style, if you want to do some physics stuff too, that's perfectly fine. I think it'd be kind of neat to have a whole bunch of physics streamers, but it doesn't make sense because physics is like, you can only really do numerical work. So even if we had a science hashtag, like a general science hashtag, or community on Twitch Creative, it wouldn't make that much sense because there aren't that many scientists here either. Anyway, that was a long discussion for nothing. But again, let me know your feedback. I'm really interested to hear it. And now let's go through and see where this guy actually breaks. Does it get through? Let me see. So size t less than row number. Again, in this case, row number is 5. Let's see how far we get with the K's. Hashtag simulation would work, I guess. But the problem is, with simulation, a lot of people when you're doing simulation want to do like, I don't know, they're like weird simulations, like popular simulations, like there's this subreddit called R Simulated, and you go to R Simulated, they have what is it? They have like, I don't know, it's just like worms falling or something like that. Like it's all in Blender, and it's not like simulations. It's like, you know, physics engines. It's weird. So let me go ahead and do this real quick. I'm going to say J2 equals the following, and then we're going to say J one more time. And now we go down here, and we're going to say K equals. So we're going to do std cout, and we're going to say K equals K. Oh, sorry about that. K, end line. And let's do G++. A dot out. How far do we get? So we get to, I think, what do we get to? Does it actually break after this? Let me do a real quick C out here. STD, C out. I'm gonna feel real bad if we get through here. C out, finished. Normalize? It's not normalizing. Finished. Scaling. R. And end line. G++. Oh, what did I do? Oh, I forgot a semicolon. Let's go here. Over here. G++. Alright, Dave, see you around. Have a fantastic day. Okay, we actually got through scaling R. So all of this, which I put down here because I thought we screwed up in scaling R, we were fine. Okay, so let's just do this. Okay, and now we know that the error is below this, so it is in one of these guys. Let me say, 1 second. STD cout, checked diagonals. Oh, cool. Added a semicolon on accident. G++. A dot out. What? Okay, if diag row equals 0. Diag row equals row num. Let's comment this guy out. G++, A dot out. Well, that ran. Row diagonal of row number. Maybe they need a -1 on all of these guys. I would guess, maybe. Let's just add a -1 to these guys. Why not? And then we'll check that later. Okay, so now we're gonna say let's do the -1 is needs verification. Okay, let's go over here. G++, A dot out. Okay, the -1 needs verification, but at this point we do have a good skeleton to work with. It's probably just a matter of getting the indices wrong and checking things to make sure all that is set. So let's go in and go ahead and git commit landzos.cpp, and we're going to say, oops, sorry about that, added skeleton of QR decomposition for testing. Okay, right quit. Git push. Let's say origin master, I guess, because we're on Simuleos. I really should have a beta branch, but hey, who cares? It's a dirty master. Okay, and at this point, guys, if you go to my stream, you scroll down a little bit to the very bottom here, you'll see we have a GitHub account there. It'll bring you directly to Laos. If you go to Simuleos, you will see under DMRG, landzos.cpp, all the changes we made today. And again, it's a lot of changes. We got pretty far today, and I'm pretty excited about that. But it's 7 o'clock in the morning. This is about the time I typically end my stream. So guys, have a great day, night, afternoon, morning, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where we work on this again. Make sure QR decomposition is actually working, which at this point I'm not confident in saying it will, because again, after taking a full day of actually coding it up, the chances of it actually working are like slim to none. So we'll work on that this afternoon, or I'll work on this afternoon. Tomorrow morning, we should see if it works. And then tomorrow, we'll actually be implementing what I mentioned at the start of this video, which was the power method, which is how we're actually going to diagonalize this system. With that, guys, thanks so much for watching, and I will see you next time. Bye, guys. Have a great day.